Welcome to problem solving session for the course Linear Algebra. I am Siddhi Balu Ambore from IIT Gandhinagar, and today we will discuss problems related to various topics across the course. And let us start with what we left last time. So the question was, um, yes, so the question was, let A be Aij, a matrix in M and R, be n cross n matrix over real numbers. And suppose that we have this condition for each I from 1 to n, that is for each n, we have this condition that this aii, the diagonal entry, ith diagonal entry, the mod of that is greater than equal to the summation of rest of the entries in that row. Then we have this, that a1, this product a11, a and n, determinant of a is greater than 0. And we can check, we discussed this, we can clearly see that this, from this condition itself, from given condition, if we call this condition, this one as star, condition star, we can see that this AIIs are non-zero. Okay. And we also saw this in last session, that is week 12 session, session, that determinant of A is non-zero. We also proved this. This is proved in what you can say, week 12 live session, and the last question which we were discussing. So it's been already proved in week 12's class, and the station. And so we have to now prove this part, that this product of a1 to an, determinant of a, is greater than 0. So see, first we have to check that it's non-zero, right? And the AIs are non-zero from the condition itself, we can see. And determinant of a is non-zero is what we have already proved. Just check one. Hello? Yeah. So that's there. So now we have to check that whether the determinant is positive or not. That's what we want to check now. So we will do this, that now, so we have, so hence this determinant of, this a11, a22, a determinant of a is definitely non-zero. That's what we know. Now to check that this determinant is positive, this whatever this number is, a22, a and n, determinant of a is greater than 0. This is what we have to check. Okay, so what we do is we consider this diagonal matrix. Consider the diagonal matrix D, diagonal of a11, a22, the diagonal of a matrix which is given to us. Okay, which has the same diagonal entries as A, because we and zeros of diagonal and zeros of the diagonal. So this is there, and clearly this D also satisfies this condition clearly. So this condition here is called as diagonally dominant. We say that A, um, yeah. Okay, so matrix A is called diagonally dominant if it satisfies this property. Um, so if A has star, then A is diagonally dominant. Okay, so this is what we have. And clearly this D is also diagonally dominant. D is also diagonally dominant because rest all entries here are off diagonal. So D is basically like this, A11, A22, and rest are all ANN, and rest are all 0. So anyway, the sum this, and we know this AII is non-zero, so mod AII will strictly be greater than 0 for all I from 1 to n. Okay, so this will be there. Uh, so this D also has this property that it is strictly, in fact, this is strictly diagonally dominant, that this inequality here is strict. Okay, so it's there, and now what we do is we define this family of matrices. So we define this family of matrices parameterized by T in 0 to 1, such that AT is 1 minus TD plus TA. So if you know, then this is kind of path between D and A. So at 0, the matrix is D, and it smoothly goes to A when T is 1. So this is kind of path in the space of matrices joining D to A. So it starts from T and it ends at A. Okay, starts at D and ends at A. So that is at T is equal to 0. This A of T, that is A of 0, is D, and at T is equal to 1, this A of T is A of 1, that is, we can say it will be A. Okay, these two information is what we have. And for how entries of ATs, if we check, then at is diagonal entries are AIIT, that is 1 minus T AII plus TAII, right? So we are just following this formula here. And we can see that then this is just AII, right? Because this minus TII plus TII gets cancelled. And this off diagonal entries, it is AIJ T. So that is 1 minus T AIJ, which will be 0 since D has off diagonal entries 0, plus T AIJ. So this is just T AIJ, since D or DIJ is no, is 0 in D. Or let me write this explicitly. Off diagonal entries of D are 0. Okay. So we have this information. So it at each entry of AT, or each entry of this matrices, it is smooth function. So if I look at this AT, so we have this AT, right? Parameterized with AT. So if I look at this function A ijt, this is smooth function which is starting from the entry of D and it ends at the entry of A. Okay, and we can see that. And yes, so and each of this function is continuous. So each of this, so this diagonal entry, this AIIT, for diagonal entries, it is just constant AII. And for rest other no off diagonal entry, it is TAIJ. So it is again a continuous polynomial at off diagonal entry. Okay, so understand that this, when I write this AT as a matrix with T in it, it becomes a polynomial at each entry. And these are exactly the expression of those polynomial. It is just AII at diagonal and TAIJ at off diagonal entries. So, so we have this. So now we check that we show that this, we check that uh, this AT, the matrix AT for T in 0, 1 is also a strictly diagonally dominant matrix. Okay, so for each, so what we have to check for each row I, what we have is summation j not equal to I will be what? It will be this TAIJ, right? Mod of TAIJ or AIJT, whatever. AIJT, if you want to write it. That is just summation A not equal to J not equal to I mod of TAIJ. That's what we calculated, that this AIJT. So when I'm writing this AT, I'm looking at it as like this, AIJT. Okay, that's why I'm writing it like that. So, but then this T gets common because it's there in every term. J not equal to I mod AIJ. Okay, we have this so far, but this will be less than equal to summation J not equal to I mod AIJ because T is between 0 and 1. So we have this information, and this is anyway strictly dominated by mod AII, right? And this is nothing but mod of AIIT. This is what we calculated here, that AIIT is AII. And that's what we got here. Okay, so this implies this summation j not equal to I mod of AIJT is strictly less than mod AIIT. Okay, so therefore this shows that therefore this AT is also a strictly diagonally dominant for each T in 0 to 1. Okay, so we have this condition here, and this inequality remains strict for every T in 0 to 1 because D at 0 has diagonal matrix D, which is diagonally dominant. At T is equal to 1 also we have A, which is anyway diagonally dominant from the given condition. So, and we can also, so the same argument which we used for checking that determinant of A is non-zero, we can use the same argument to check that determinant of AT is also non-zero. So we can use the same argument to prove that determinant of A T is non-zero. Okay, we can follow the same argument. We can start with the non-zero vector, suppose in Rx. So what we do is, if you remember, the quick argument was we start with this linear transformation. This AT, x going to ATX for each t. Okay, for each t, when I want to check the determinant of AT is non-zero, though I'm writing it in general form, when I'm writing this expression here, the t is kind of fixed. I'm taking so this I will start with this linear transformation, and if this linear transformation has non-trivial kernel, then I choose this if 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 this linear transformation, if I call this linear transformation suppose T, if T has non-zero kernel, then what I have is, then there exists x1 to xn in Rn such that I will have this ai sorry this a such that it will become zero, such that this ATX becomes zero matrix. Okay, and what does this mean? Then the each row of this matrix becomes a, then the ith row of ATX is AI1 TX1 plus AI2 TX2. It is the same argument which we followed, AI n txn, this will be 0. And since this x, since we are talking about non-zero kernel, then this x we can choose a non-zero in Rn. And since this x is non-zero, we can choose the I such that mod xi is maximized or is largest among all these entries of xi in X, maximized, that is this mod xj is maximum, sorry, mod xi is maximum of j, mod xj, and this is anyway, this will be strictly greater than 0. So for this I, this maximized I will have this a I t xi will be summation. So I'm just what I'm seeing. I'm just using this formula here, and what the statement we got. This will be minus of aij txj. And so this will imply that mod of this aiit xi will be minus of j not equal to 1 aij txj. Mod of this thing minus goes, and this becomes mod aii into mod xi. Okay, AIIT is anyway AII here. So which will be less than equal to summation j not equal to I mod aij t and mod xi j. And since we know this is diagonally, since this mod xj is less than equal to mod xi for all j, this becomes that this aii mod xi is less than equal to summation j not equal to 1 mod aij t mod xi. Now this, I mean, we are going from here to here with this inequality. Okay, and then this will imply that mod, since and this xi is non-zero. Okay, we are looking at a non-zero vector and we are taking the maximum among those entries, the modulus with maximum modulus. So this mod xi is non-zero, so I can just remove it. So I get summation aii less than equal to summation j not equal to 1 a ijt. And this contradicts this fact which we just proved. If I call this star star AIIT, I switched this. We can just skip AIIT, does not matter. This contradicts star star, which we just proved that ATT is diagonally dominant matrix. Okay, so this therefore determinant of AT is non-zero for all t in 0, 1. Okay. Determinant of D is non-zero for t is equal to 0 because each entry is aii which is non-zero from the given condition. Determinant of A is non-zero is already we proved last time. The same argument, just drop this t, and this is the same argument which we will need, which we use to prove that. Sorry, this here. That determinant of A is non-zero, and we are now using the same technique to prove that determinant of AT is non-zero for each t. Okay, so if and understand that this, since each entry of this AT is polynomial, the note that the determinant of AT is a continuous function of t. Okay, because each entry is a polynomial, and when we calculate its determinant, it again becomes a polynomial. Okay, so the determinant is a polynomial function of matrix entries. We know this, right? And each entry aijt is continuous function. In fact, this is continuous. This is linear polynomial, in fact. Let me just write clearly, linear polynomial in T, okay? So therefore, therefore, this determinant of AT is a polynomial in T. And hence a continuous function, and hence continuous function of T. Okay, on 0, 1. So since AT is now continuous function and is never zero on the interval 0, 1, it must have constant sign throughout the determinant of AT. See this determinant of AT. Determinant of AT is non-zero, we know, and it is continuous function, we just checked, and it is non-zero function throughout on the interval 0 to 1, so it must have constant sign. Okay, the intermediate value theorem we can check. Okay, so it will have constant sign throughout. So if determinant of AT at 0 is positive, then throughout does not matter whatever value it take between 0 to 1, it will remain positive. If determinant of AT at t is equal to 0 is negative, the determinant will remain negative throughout the interval t from 0 to 1. So it must have constant sign throughout the interval 0, 1. Okay, you can by intermediate value theorem. So so it's enough to check the sign of t at 0, right? So hence it is enough to check sign at t is equal to 0. Okay, because t is equal to 0, it gives me d. So we just have to check whether determinant of d or the determinant of at at t is equal to 0 is positive or not. Okay, because the sign will remain throughout constant, and at t is equal to 1, we will get determinant of at will be determinant of a, and we will get the sign. So so now observe that we compute the sign at t is equal to 0 and relate it to t is equal to 1. Since the sign remains constant throughout, at t is equal to 0, a of 0 is d. So determinant of a of 0 is determinant of d. That is this, right? Just a11, a22, a okay. Now at t is equal to 1, a of 1 will be a. So determinant of a of 1 will be determinant of a, and that's it. So if so hence if I'll call this as this this one as this star. I'll just use some other color if you want. This green star. So hence by star, sign of a11 sign of determinant of a0 and determinant of A1 is same, we get that determinant of A 0 into determinant of A1 will be greater than 0, is same and non-zero. We will get this because if determinant of A0 is negative, determinant of A1 will also be negative using this star which we have here. And if determinant of A1 is positive, then determinant of A0 will also be positive, and I mean both will have same sign. So, but what was determinant of A0? It was just A11, A22, ANN, and determinant of A1 was just determinant of A, and we got this to, and it will be greater than 0. So what? So I hope this will be. Okay, so this will be positive hence. Does not matter what we. So these two have same sign. These two have same sign using, I sorry. These two have same sign, A0. This A0 and A1 has the same sign. And their product is in fact this term, A11, A22, AN, and determinant of A. And we saw that since they both have same sign and both of them are non-negative, both of them are non-zero. If A0 has negative sign, A determinant of A1 will also have negative sign. And I mean using this green star here. Okay, and similarly, if determinant of A0 has positive sign, the determinant of A1 will also have sign positive sign, and so this their product will be positive in general. Okay, because they both have same sign. So same sign, two terms will always give positive product when they are non-zero. Okay, so hence this is what we wanted to prove, and it's proved now that this will always be positive. Okay, we use this intermediate value theorem here to conclude this, okay? Uh, we'll move to next question now. This question is related to permutation group. So question 2, that show that subgroup U of the permutation group Sn, which contains odd permutation, contains the same number of odd permutations as the number of even permutations. So what this statement says is that if U is a subgroup of permutation group and if U has odd permutation, okay? If U does not have odd permutations, we do not care about that. But if U has odd permutation, then the number of odd permutations in U will be equal to the number of odd permutations, number of even permutations in U. That's what the statement means. Okay, so I'll note that. Uh, the statement talks about subgroup U of Sn when U has at least one OR permutation. Okay, and OR permutation, and if U has odd permutation, then number of odd permutations in U is equal to number of even permutations in U. This is what statement means. Because we have alternating group or this group of all even permutations in Sn. Okay, it does not have any odd cycle, odd permutation. So yes, so when we are saying this statement actually talks about subgroups which has odd permutation. We do not care about permutation subgroups which does not have odd permutations. Okay. So let us start with this. So let U subset of Sn be a subgroup of Sn uh, containing at least one odd permutation. Okay, and we denote, let us denote this EU as the set of permutations is in U such that their sign is positive. That is, it is just collection of all the set of even permutation in U. Okay, and OU is although sigma in U such that sign of sigma is -1. Okay, that is the set of all odd permutation in U. Okay, so we have to show that what we have to show is now that cardinality of OU, that is number of odd permutations, is equal to number of even permutations in U. Okay, so note that the sign function, the sign function from Sn to +1 -1 is a group homomorphism, right? That is, it satisfies that sign of sigma tau is equal to sign of sigma, sign of tau. This is what we know. It is group homomorphism. And this group is just the subgroup of R under multiplication. This is multiplication group. Okay. Uh, so we have this information with us that this sign function is group homomorphism, and kernel of this group homomorphism is kernel of this sign function is In fact, although sigma in S is such that sine of sigma is 1, and this is nothing but our an. Okay, the alternating group which we have. So this is just for understanding that sine function is group homomorphism, and it follows this property, and its kernel is an. So, and now the second thing is understand this, that for since U is subgroup, it is closed under closed under composition, that is our multiplication in Sn, and inverses, right? I mean the inverses of U and product of elements in U again belongs to U. That's what we have because U is a subgroup. So hence if sigma belongs to U is odd, then for any tau in U, the permutation sigma tau has the sine of sigma tau is equal to sine of sigma into sine of tau. That is, but sigma I chose to be odd permutation, so it will be -1 sine of tau. Okay, so if tau is even permutation, then sigma tau is odd, and if tau is odd, this implies that sigma tau is even, right? And the inverses, the inverse sigma inverse has the same sign as a sigma, since sine of sigma inverse is sine of sigma. So we have this because since sine of sigma into sine of sigma inverse, we know that sigma inverse is E, and so sine of sigma into sine of sigma inverse will be 1 because sine of or +1. So both of them must have same sign. Okay, the same argument which we just used few minutes back to conclude that product of a1 to an and determinant of a is positive and so on. So they both have same sign. This is also what we know. So if I have a odd permutation, when I multiply it by any permutation from U, if it's even permutation, it will give me odd permutation. If it was odd permutation, it will give me even permutation. And also sigma is such that its inverse also have same sign. So what we do is we define, so we construct this bijection. We define the map, this phi from EU to OU. Okay, the set of all even cycles to odd cycles. So we fix sigma belongs to U such that sigma is odd permutation. And we define the map EU to OU such that any tau here goes to sigma tau. Because note that every permutation here is even. And we saw that when I multiply even permutation with odd permutation, I get odd permutation. So for any even permutation EU, I will have this odd permutation OU from U. Okay. So this map is well defined because so the map is well defined. The map is well defined. Okay, because if tau belongs to EU, then sign of sigma tau will be sign of sigma and sign of tau. And this one is plus, this one is -1. Tau is in EU, so +1. And I get ultimately -1, which implies that this sigma tau belongs to OU. So it is well defined map. That's not a problem. Uh, so now we will check the injectivity of this map. And so suppose I have phi of tau, let tau1 and tau2 belongs to EU. Okay, is equal to phi of tau2. So this implies that sigma tau1 is equal to sigma tau2. Okay, but sigma belongs to Sn. Hence, this implies that sigma inverse belong to Sn. So this will imply that sigma inverse sigma tau1 is equal to sigma inverse sigma tau1. So since sigma tau1 is equal to sigma tau2, I will have this, and this will give me tau1 is equal to tau2, right? The product. So therefore what we got is, we have that sigma tau1 is equal to sigma tau2 implies tau1 is equal to tau2. So therefore it is injective. Therefore this phi is injective. Okay, and we also have to prove surjective because uh, these two are different sets. So in order to prove they are bijective, we have to prove both injectivity and surjectivity. So let this omega belongs to OU, that is, let this omega be some odd permutation in U. We need to find now tau in EU such that this phi of tau is this omega. That's what it means to check the given function is surjective. Okay, so we set okay, so that is what we want is that sigma tau to be omega. That's what I want. So we set tau to be sigma inverse omega. Okay, then note that since omega belongs to OU, it is odd permutation. And sigma also belongs to OU, therefore odd permutation. And since sigma is odd permutation, this implies that sigma inverse is odd permutation. So therefore, this sigma inverse omega This implies this sigma inverse omega is even permutation, product of two odd permutation. Okay, so therefore this tau belongs to EU, which is domain of our function P. So therefore this phi of tau, that is phi of sigma inverse omega, is sigma of sigma inverse omega, that is sigma inverse omega, that is omega which we got. Okay, so we have this, therefore tau is equal to sigma inverse omega belongs to EU. So therefore this, for omega in OU was arbitrary, and I could find a even permutation such that their product, no, even permutation such that its image under phi is omega. Okay, so therefore I have, therefore phi is surjective. Okay, and since both this EU and OU are finite sets, and phi from EU to OU is bijection, this implies that cardinality of EU must be equal to cardinality of OU. Okay, this thing is important here. Okay, so hence such that tau going to see. We proved that the number of even and odd permutation in both the sets are same. So this was a statement which shows I hope this was okay. I mean, so this is the statement which we prove. So the statement was that if U is a subgroup having odd permutation, then it will also have even permutation. So let us do this one question. Question 3. That the matrix of endomorphism F from Q3 to Q3 with respect to the standard basis E1, E2, E3 of Q3 is matrix zero one one, 101, and 110. Okay, and we have to show that the vectors E1 minus E2 minus E3, 2E2 minus E3, and E1 plus E2 for a basis of Q3, and we are asked to write the matrix of F with respect to this basis. So we are asked two questions. First the matrix of F is given in terms of E1, E2, E3, and we are asked to check whether this set here, whether it forms a basis of Q3 or not. Uh, and we have to now then give the matrix of F with respect to this basis. This basis means this basis here. By this, it means this basis. So first, let us check that whether it forms a basis or not. So let us denote this first. First, let us see how these elements look like. So let V1 is equal to E1 minus E2 minus E3. So that is 1, 0, 0 minus 0, 1, 0 minus 0, 0, 1. That is 1 comma minus 1 comma minus 1. My V2 is 2 E2 minus E3. That is 2, 0, 1, 0 minus 0, 0, 1. That is 0 minus 0, 2 minus 1. And my third V3 is E1 plus E2. So this is 1, 0, 0 plus 0, 1, 0. That is 1, 1, 0. Okay. So to check, uh, if V1, V2, V3 form a basis of Q3, we need to check. We need to check whether they are linearly independent, because we don't need to check span. We know the dimension of Q3 is 3. So we have 3 vectors. So if they are linearly independent, then they will form a basis. So we know these statements, right? That a linearly independent set of the cardinality of dimension will form a basis of that vector space. And if a given set is generating set for given vector space, then its cardinality will at least be dimension. Okay, so the basis is minimal linearly independent uh, set which generates V. Minimal with respect to cardinality. Okay, so if something generates the vector space, it has to have a cardinality at least equal to dimension. And if a set is linearly independent, the maximum cardinality it can have is the dimension. Okay, and here we have 3 vectors which so these three vectors, that is we have a set of cardinality equal to the dimension of given vector space. So to conclude that this is a basis, it is enough to check that it is a linearly independent set. So that's what we will be doing. So we need to check whether uh, V1 to V3 is a linearly independent set. Okay, so it is enough to check whether, so it is enough to check uh, the whether the matrix P with columns as coordinates of V1, V2, V3 is invertible or not. And note that this P is a basis change matrix from standard basis to this V1, V2, V3. If we conclude, okay, so this comes later. First we have to check, sorry, this comes later, actually. So let P be this 1 minus 1 minus 1, 0 2 minus 1, 1 1 0. This is my coordinates of this vector v1 v2 v3 are, and determinant of P is, will calculate it with respect to first row. So 1 plus 1 plus 0 plus 1 into 1 plus 2. So it is 1 plus 3. So that is 4. So this is non-zero. Therefore, P is invertible, and hence this v1, v2, v3 is a basis of Q3. And note that this P is a basis change matrix from standard basis to V3. Okay, because this is E1, E2, E3, coordinates of E1, E2, E3. And this is my V1, V2, V3. So this is basis change matrix, standard basis. Suppose if I call it E, and if I call this, not V, whatever, if I call this as beta and I call this as beta dash, this is beta, beta dash. And so I do not know whether you know this or not, but if I call this as beta and this as epsilon and this as beta. Okay, so if the matrix of F, so now we have to calculate. So we were asked two things, that to check that this V1, V2, V3 forms basis of Q3, and the second thing which we were asked was to give the uh, matrix of F in terms of this V. Okay, so the matrix of F with respect to epsilon, that is the standard basis E1, E2, E3, is this, right? The given matrix. That was this matrix. Sorry. Okay, if we call this, suppose A. Okay, so to find, so then the matrix of F with respect to the basis beta will be P, that is this, if I call this matrix P, will be, let me write this explicitly, that matrix of F with respect to standard basis into matrix, this basis matrix from epsilon to beta and its inverse. How to, yeah, this is identity. This is identity, right? So understand this. Oh, sorry, this inverse, the whole inverse. I mean, that's the same thing, what I wrote there. This epsilon beta inverse, and this we yesterday saw that it is inverse of this matrix. This is exactly this beta epsilon. So what we need to do is, yeah, so what we need to do is, hence, the matrix of F with respect to beta will be this P A P inverse A P. Okay, so we already have P. So what we have to do is we have to find the inverse of this P. So there are various methods you can use to obtain. Sorry. Inverse of this matrix P. So hence we need to calculate the inverse of matrix P. Okay. And there are various methods we can do. We can either form this row operation method, or we can do the finding cofactor matrix, adjoint matrix, and the determinant inverse. Okay. So we already have the information about determinant of P. So we will do this using, because we did not do it even once in our live sessions. So we'll do it using the cofactor, finding cofactor matrix and everything. So we have determinant, we already calculate that determinant of P is 4. So therefore determinant of uh, P inverse will be 1 by determinant of P. So that is 1 by 4. That is there. And so cofactors, we will calculate the cofactors. So C11 will be, so, let me just write this P quickly here. This is P. So cofactor C11 will be, we are removing this and this. So whatever is left, matrix determinant of this 2, 1, minus 1, 0, that is just 1. Okay. C2 will be, sorry, C12 will be, we are removing this and this, and determinant will of this will be minus 1, minus 1, 1, 0, and this will again be 1. Oh, we also have to take these powers, corresponding powers, yeah. Minus 1 power 1 plus 1, minus 1 power 1 plus 2. So this is 1 into 1. And therefore 1. This is minus 1 into 1, that is minus 1. And C13 will be minus 1 power 1 plus 3, determinant of this thing, that is minus 1, 2, -1, and that is equal to 1 into 1 minus 2, 1 plus 2, that is 3. And C now 2, 1 will be minus 1 power 2 plus 1, and that is, you can check this, okay? I mean, I'm not drawing everything here. It will be 0, 1, -1, 0, and this will be -1, and this will be 1. So this will give me -1. C2, 2 will be -1 power 2 plus 2, and it will be 1, 1, -1, 0, and this will give me 1 into 1, that will be 1. C2, 3 will be -1 power 2 plus 3 into determinant. 2, 3 will be 1, 0, -1, -1. So this will be -1, giving me 1. And C3, 1 will be -1 power 3 plus 1, 0, 1, 2, 1. And this will be plus 1 into -2. So this will be -2. And C3, 2 will be -1 power 3 plus 2. And this will be 1 minus 1, 1, 1. This is -1 into 2. That will give me -2 again. I hope I wrote this correct. For 3, 2, it will be. Did I write the last entry correctly? Three, 2 will be this, right? Let us do this 3 plus 3. And determinant is just 1 minus 1, 0, 2. 1. I hope this was correct. Okay, where is it? And it is plus 1. I hope I am not making any mistake here. And 2, this will give me. This is correct. This is 2, that is 2. So I get this cofactor matrix of P as this matrix 1 minus 1, 3, 1 minus 1, 3, minus 1, 1, 1, and -2, -2, 2. I hope I'm still correct. Here I have 1 plus 1. It's correct. So adjoint matrix of P will be just transpose of cofactor matrix. And this will give me 1 minus 1, 3, minus 1, 1, 1, and -2, -2, 2. And so therefore, this P inverse will be 1 by 4. This 1 minus 1 minus 2, minus 1, 1, -2, 3, 1, 2. Okay, so So this B is my P inverse AP. That is 1 by 4 this matrix into A, and I have P here. So we just have to multiply these three matrices and we will get what we wanted. So this is 1 by 4. Let this be as it is. Minus 2, 1, 1. This is 0, minus 1, 1, 0, 2, 1. Okay, and finally this one. It is minus 2. So minus 2, 1 plus 1, minus 4. So 2 minus 4 will be minus 2. I might make some mistakes, okay? Please. If this calculation I'm doing, so this will be 1 minus 1 minus 2. So this will be just minus 2. This will be 2. Minus 1 minus 1 minus 2. Minus 4, that is 2. And this will be mm, minus 2 again. And the final one will be this minus 6. 3 minus 1, 2 plus 4, that is 8. And final one will be 6 again. Okay, so this is the required matrix which we wanted. And let me just check. Okay, so this is the required matrix divided by 1 by 4, and we will get 1 minus 1 by 2 minus 1 by 2 minus 1 by 2. Sorry, yeah. Then 1 by 2, 1 by 2 minus 1 by 2 minus 3 by 2, 2, and then 3 by 2. This is matrix B. This is matrix of F with respect to V1, V2, and V3. Okay, so I hope this was fine. And that's it. That was it. That's what we were asked to do. Let us move to next question. Yes, let us do this one. That the basis, I think this is question number 4. Yeah. The basis E11, E11, 1 to E1n, E, and so on till EM1, EMN, and E11 up to EM1. So, and E1n up to EMN represent the same orientation of M and N. So this is M cross N matrices over R, if and only if this M choose 2 and N choose 2 is even. This is what we are asked to prove. So see, these are two bases of M n cross. So note that here Eij is this matrix, ith, sorry, jth column. This is ith row. And so here it is 1, rest all are zeros. This forms basis of M MNR, MMNR. Okay, so all M cross N matrices of over R. So this is what Eij is. So they have place. So when we talk about orientation, as we also discussed, that orientation requires the ordered basis. Okay, we change the order and the determinant changes with respect to standard basis, and it no longer remains in the same orientation. The orientation changes, the sign of the matrix changes, and hence the orientation changes. So yeah, for basis change matrix, so I hope you know what orientation means. So orientations of Rn, it's just partition of basis in two forms. Like we consider the standard basis to have positive orientation, and if a basis change matrix from standard basis to given basis. So for a given basis, the basis change matrix, if it has positive determinant, then we say that it has the same orientation as standard basis, that is positive orientation or standard orientation. And if it has negative orientation, then we say that that matrix has negative orientation, or it does not belong to the orientation class of standard basis. And we can check this for two bases, whether they belong to same orientation class or not. So if beta and beta dash are two bases, we say that they belong to same orientation class if their determinant of basis change matrix from beta to beta dash has a positive determinant. If it has positive determinant, we say that they belong to same orientation. They have same orientation. And if the determinant is negative, we say that they have different orientation. So yes, so we have now these two bases. If we call this as beta, and if we call this as beta dash or b dash, we have to check whether they have same orientation or not. We do not have to check that. They are saying that they will have same orientation if and only if this m choose n and m choose n, this is number. This number here is even. Okay. And so let us see how the elements in the B1 look like. So they are calling this B1 and B2. So we will do the same. So the the first basis B1 is row major, has row major order. So that is the order is first we are taking care of all the rows. Okay, so will you will understand what it means. So it is E11, E1n. Okay, so it is taking so what it does is it is taking care of all the first row. So E11 means basis corresponding to this entry. E22 means basis corresponding to E12 means basis corresponding to second entry and third entry and so on. So E1n means basis corresponding to first to last entry. So row major means it is first aligning basis element as it is generating first row first. Then it is aligning all the elements containing second row, third row, and so on, and then the mth row. Okay, so that's what it row major means. So the basis is arranged such that uh, the first n elements give give me information about first row. Okay, so that's what a row major order means. So second is this E21, E22, and E2n, and it goes so on up to EM1, EM2, and EMN. Okay, so the position of ERC is in B1 is R minus 1n plus C, right? Because see, R means R, we are talking about R, uh, the entry corresponding to rth row and cth column, right? So for it to reach our rows, so for first row, if it was 1C, so it will be in the first row and plus C, right? So it is dealing with first n element. So it will be just cth term here. So R minus 1 will be C, right? And then after first row is taken care of, n elements are done. And for the second row, E2C, I am getting now, I have to check for n plus 1, n plus 2, and then n plus C position will have E2C as its element in basis. So therefore, when I have Rth, I have to take care of Rth row basis. I hope you understand when I say rth row basis means it means the one corresponding to element entries in rth row. So ERC, it will have to omit first R minus 1 into n terms, then it will start to take care of R minus 1 rth row, and then it will give me the cth term. So for example, E1, 2 is in the second position. E24 will be n plus 1, 2, 3, and fourth position it will be. So it will be n plus 2, n plus 4. And this n is coefficient, has 1, that is r minus 1. Okay, and here r was my 2. Okay, so I hope you understand what I mean here. Okay, so that's how it is done. And we know in this, so since this is ordered basis, we need to know at what position the given basis element is placed in that basis. That's what we are trying to understand. And similarly for second basis, the second basis B2 is column measure. So it is first taking care of all the columns. So basis which corresponding to columns first, and I mean it takes care of first column, then move to second column and so on. So it is E11, E21, E N1, and then A 12, E 22, E M2, sorry, not M2, N2, and so on. And then it goes to E. Oh, we have M columns, right? We have N column. So it is correct. Oh, sorry, we have M rows only. Rows are M. So yeah, this will be M2, this will be E M1, and then we are going to Mn. So these are M rows. Sorry, these are M rows. Let me write here N columns. And the position of ERC in B2 is, now note that now we are first taking M. So what changing here is the columns, right? The number of columns here. So the C is changing. So first we have M rows. So when I have to move to, so this will be this. Let me write this C minus 1 M plus R. Because see, to go to Cth position here, I first have to omit first C terms, which are taking care of first C columns. Okay. So I have to first omit those many C minus 1. So for example, 1C, if I want to look at 1C, or yeah, 1C term here, then this is in first row and C position. So I have to omit this C minus 1 rows first, right? And then the next will be the C position here. And the first entry will be this. So MR, so so for example, if I have something here which is in ith row, so first I have to omit this M elements, then this M elements, then these are M into I minus 1, right? And then here I am looking at which row I am talking about. So for example, if my element is EIC, for example, this is ith column, right? So I'm talking about ith column, and for example J. So I first have to omit this I minus 1 columns, and then in this ith column I will go from 1 2 3 4, and this will be my jth position. So this will be M minus I minus 1 into M plus whatever I am getting here R. So this ERC, when I look at it in terms of ERC, this is MI, this is just C here corresponding to I. So this is C minus 1, M as it is, and R corresponding to J. So that's what we have been doing. Uh, so I hope you understand what it means. So where the position of particular basis is basic, what I can say, the basis element is when we talk about B1 and B2 both. Okay, so now we have to change the basis from B1 to B2. Okay, so we have to check whether they both have same orientation or not. So we have to calculate their basis change matrix. So the change of basis or basis change matrix from B1 to B2 is a permutation matrix for the permutation, sorry, yes, sigma belong to Smn. There are Mn elements such that where this sigma C minus 1 M plus R is going to sigma C minus 1 sigma this element. We are going from B1 to B2. Okay. So this is going to R minus 1 N plus C. Okay, so the columns are corresponding to B1 and the rows are corresponding to B2. So columns are corresponding to this. So the column is taken care by C minus 1 M plus R, and these are taken, and this is what entry at that row it will be. So to find, so the sign of this matrix will be sign of this sigma and sign of sigma. So what the sign of sigma is will give us whether the determinant of this basis change matrix beta 1 to beta 2 is what we say has same sign or not. So to find the sign of sigma, we compute the number of inversions of inversion pairs, inversions that is pair k less than L such that sigma of k is greater than sigma of L. Okay, and this equals the number of pairs of distinct basis elements that are ordered differently in B1 and B2, right? Because see, not everything is inverted here, not everything is shuffled. Okay, for example, E11 remains as it is, EMN remains as it is. So we have to check like what are the elements which have not. So I hope you understand what inversions means. It is understanding how differently or I mean how disturbed the what we say sigma is in terms of order. So if k is less than L, so I'm looking at whether where the sigma L is greater than sigma k is greater than sigma L. Okay, so how much disoriented my sigma is, that's what we check when we look at inversions. So the label element, so the we label the label elements by pair RC, and order in B1 is lexicographic. Okay, I hope you know what lexicographic order means. So lexicographic order means in tuple we check for first inequality, then second inequality, and third. I mean lexicography is also taxi uh, cab order. Okay, so I mean I hope you know what lexicographic order is. So lexicographic order means if I say A1 to AN is less than B1 to BN, this implies that uh, this that if I is least such that AI not equal to BI and AI is less than BI. Okay, this is under lexicographic order. This is my lexicographic order. This is also called as dictionary order. Yes. So yeah, so this is lexicographic order on RC, and order in B2 is lexicographic order, lexicographic on CR, right? So for element RC, for the label RC, B1 has lexicographic order on RC and B2 has lexicographic order on CR because in CR we are first taking care of. So the column here is first taken care and then the rows are taken care in B2 as it is column dominant. I mean, what we said that column major. And for rows, the RC will remain at RC position under lexicographic order. It won't change. Okay, so two elements. R1 C1 not equal to R2 C2. Uh, Disagree if their relative order differs. Okay, so this occurs only if R1 not equal to R2 and C1 not equal to C2. And specifically when R1 minus R2 and C1 minus C2 have opposite signs. Okay, I hope you understand. This occurs only if R1 and R2 are not equal. Both of them are not equal. Uh, and if their relative order differs. Okay, so this occurs only if this R1. So what they are saying is that these two are not equal if both of them are not equal. Okay, if both of them are same, then the matrix, the element becomes same. Okay, so this occurs when R1 is not equal to R2 and C1 is not equal to C2. And then when R1 minus R2 and C1 minus C2 has opposite sign. That is, if, for example, if this is 1, 2 and 1, 3, for example, uh, this if we are talking about in B1, so this is how it is placed in B1. And similarly in B2, it will be placed second column first. So this will be again placed like this. So what they are saying is this will be completely, so when this kind of situation is there, when at least one of them is equal, their ordering remains same. In for example, if I also talk about 3 2 and 3 4, for example, it will still be like this in both B1 and B2, the position of this will be smaller than position of this. Okay, I hope you understand this. So what they are saying is, what is position of this element in B1? In B1, the position of this element is, okay, so let me just tell you this. This is R minus 1. plus n plus c, right? So this is for B1, it is r minus 1 plus n plus c, and this is c minus 1 plus m plus r, right? So in B1, the position of this will be, this is my RC, this is my RC. So r minus 1 is 2 into n. N was, suppose I am talking about 3 cross 3 matrices, does not matter. So 3 plus c is my 2. And this is again will be r minus 1, that is 2 minus 2, yeah, 2 into 3 plus 4. This will be smaller, and again c minus 1. So c is my 2. So 1 into m, that is my 3 again, plus r was 3. Yeah. And this will still be less than this one, right? C minus 1, that is 3 here, right? Yeah. So c minus 1 is 2 here. Sorry, 3 here. And then m is 3 and r was my 3 as it is. So what I'm saying is, even if even in one of them, you can check this for this one also, 1 comma 2 and 1 comma 3. And you can see that in B1 and B2, their positions are not changing. Okay, we are talking about the positioning of the matrices. So even if one of them is the same, it at least row or column I'm talking about, uh, it will always be it will be placed uh, in the lexicographic order of that tuple. Okay, so they are saying that the order completely changes. The possibility of that is happening. For example, this R1, this is R1 C1, this is R2 C2. They are saying that if they are saying that in B1 it is R1 C1 has lesser position than R2 C2, and it will have possibility to shuffle, that is switch the order in B2 only if both of them are not 0, and especially when this R1 minus R2 and C1 minus C2 will have different sign. Okay, because even if they have the same sign, they will be placed before that, right? For example, 1 1 is anyway anyway placed before 2 2 in both the cases, because in the row also it will go like it will travel like this. So in the matrix for row also it will travel like this from 1 1 to 2 2, and even in column it will travel like this. So even if, for example, if even if I am talking about something like 3 2 position will be, for example, in this matrix the 1 2 position is here and 2 3 position is here, then going from here to here it will be in the column sense, and in both in the row sense will be same. So what they are saying is, if at least one of R1 C1 R1 R2 and C1 C2 are same, then the sign does not change, or the positioning does not change, or we do not get inversion. And if both of them are smaller, I mean R1 minus R2 and C1 minus C2 is have same size, then also it does not change. For the change to occur, for the positioning to swap, we must have R1 not equal to R2 and C1 not equal to C2, and they both must have different order. For example, if I talk about something of this sort in my matrix, suppose I'm going from 3 2 to 1 4, if I have this something of this sort, then the minus, here I have minus sign, here I have plus sign. Yeah, 1 4. So how it will be? Here 3 2 will be here, 1 4 will be here. So in my row base, um, it will pass like this, right? And it will come here. From here, it will go here, and then it will come here directly. And but for column case, it is going from 3 2 to here, right? So the positioning here, 3 2 is first, then 1 4. But in row case, it is placed first, then 3 2 element. I hope you understand what I'm trying to say here. That's what this statement here means. And the number of such disagreement, the number of such this disagreeing pair is the number of ways to choose two distinct rows and two distinct columns, right? Then only this will happen. When both of them are not equal. Is this understandable? I mean, I hope you understood. I mean, you can check for these cases, and so what we need is, and so what they are saying is that we just need this. We just need this. If none of them is not equal, then we get. For example, if we have something like this, yeah, we just check for that, right? 1 1 and 2 2 case. This 1 1, and if I have 2 3, in both the cases it will travel from here to here, and even in column it will travel from here to here. So what I want is I have to choose different pairs. The number of such disagreement pairs. So yeah, that's what this statement means. So this disagreement will happen when I choose distinct this when I will choose number of way of choosing two distinct rows and two distinct columns. And and then and then take the crossed pairs. And the number of ways we can choose is this m by 2 and n by 2, right? I mean, I have to choose two rows from m rows and two columns from n columns. And that is the number of inversion. The number of disagreeing pairs means inversion in short. Okay, this is what inversion means. And the inversion pairs, the number of inversions pair is this m choose 2 and n choose 2. So therefore, this sign of sigma will be minus 1 power this, right? The number of inversions, m choose 2 and n choose 2. And this is exactly, and the sign of sigma is exactly the sign of determinant of my basis change matrix from B1 to B2. Hence, the sign of sigma, hence the basis represents, and this is sign of determinant of basis uh, change matrix. Okay, beta 1 to beta 2. Okay, beta 1 and beta 2 is just shuffling. So the corresponding basis change matrix is just corresponding permutation matrix in the rows. Okay, so the basis represent the same orientation if sign of sigma is minus 1 power m choose 2 n choose 2 is plus 1, and that to happen, and that is that this m choose 2 n choose 2 is even. And it happens both ways because I mean, this is if and only if, right? I mean, this is the signature. I mean, if when it is even, the sign will be 1, and sign will be 1 implies that this has to be even. Okay, so that's it, and that's what we were asked to prove. This sign here and these are in if and only if uh, dependency. So yes, that was it, and let's do this quick question now. One more. I think this will be, I hope this was fine. And this is question 5. Just understand this for this question and you will be okay. Okay? This part. And I think this was question 4, I think, or 5. 5. One quick question. That the basis or not. Let V be an oriented R vector space with basis V1 to Vn, and let 1 less than equal to R less than equal to N show that the basis V1 to Vn and Vr to, okay, Vr to Vr plus 1 to Vn and then V1 to Vr minus 1 represent the same orientation. It's a similar kind of question to what we did on V if either R or N is odd. Okay, so let us do this quickly and let us just understand and then. So my B is V1 to Vn represent positive orientation. Okay, so V oriented R vector space with V1 to Vn. So R has orientation V1 to Vn. So this is positive orientation by definition. Okay. And the new basis, my new basis is B dash. That is Vr plus 1 up to Vn and V1 to Vr minus 1. Okay, this is my new basis. So this is left cyclic shift, right? Because everything from left. So this is left cyclic shift because everything is shifting to the left as a whole by S is equal to R minus 1 position. Right, the permutation sigma belongs to Sn is sigma of J is equal to J plus S minus 1 mod N plus 1. N plus 1. Yeah, okay. So just depends on how you are numbering. S is equal to R minus 1 and okay, so the cycle, or I mean what I'm saying is, or if we change the indices 0 to n minus 1, this row of J will be J plus 1 mod n. Sorry, J plus S mod n. It depends on the numbering. It does not matter. Okay. And these indices. So the cycle decomposition. So the cycle decomposition of rho has d is equal to GCD S comma n cycles. Yes. And each of length n by d. Okay, you can uh, check this by using the examples, and the sign will be sign is minus 1 power n minus d. Okay, you can check this. I mean, you can take the example and you can see that the d will be GCD of S and n, and each cycle will have length n by d. And the exponents will be n minus d, because see, there are yes, since it should add to each of length n by d, right? So it should add to d, and then each cycle will have length n minus d. You can check this. Each cycle has length n minus d. Okay, so the bases represent the same orientation if minus 1 power n minus d is plus 1. That is, we want n minus d to be even. Okay, where d is GCD of this r minus 1 comma n. Okay, that's what this s was, r minus 1. Okay, and d is GCD of s comma n. That is, d is a GCD of r minus 1 comma n. So there are cases based on n odd, n even, and so on. So now we show that. Now we show this holds. Now if n is odd, then d divides n. So this will imply d is odd. Okay, so this will imply this n minus d is even. Okay, so they have positive sign. So therefore, sign of, therefore, what I can say. So n minus d is even, therefore same orientation. If n is even, then n minus d is even if and only if d is even. Right? I mean, this is basic. So now, but d is my GCD of r minus 1 comma n, and if r minus 1 is odd, then d is odd, right? So this will contradict that n is even. This implies that this r minus 1 has to be even. This implies that r minus 1 must be even. And this implies r is odd. Okay, so when n was odd, everything was fine. When n was even, we got that r is odd. And that's it. I mean, at least one of them has to be odd. So the d is even if and only if r minus 1 is even, and that is r is odd. Okay, so there were two conditions, n is odd and n is even. N is odd, we were okay. And the moment I got n to be even, r must be odd. So in both the case, we got that either n or r is odd, and that's what was asked in the question. So I hope this is fine. And so this was final. This was last live session. If you have any queries, you can still raise them on discussion forum. And those who are going to give exams, all the best to you all. And thank you.